Hello. Recall that in the previous lecture we introduced intrusion detection systems. In this lecture, we will look at different types of IDSs. IDSs can be classified in various ways. Uh, One classification is based on the detection method, that is how the IDSs detect malicious traffic. And another classification is based on where detection takes place. That is, does it take place in the network or in the host? The classification based on detection method is as follows. The IDSs are divided into two types. One is signature based systems and another is anomaly based systems. And the classification based on where detection takes place classifies IDSs into host based systems and network based systems. Let us discuss these four types of IDSs: signature based systems, anomaly based systems, host based systems, and network based systems. So we start with signature based IDSs. A signature based IDS maintains an extensive database of attack signatures. What is an attack signature? Each signature is a set of rules used to match a packet or a series of packets with a known intrusion activity. So here's an example of an attack signature. Snort is a public domain open source IDS. So you can search online for more information about Snort. Here's an example of a Snort signature. Alert ICMP $external net any arrow $home net any message ICMP ping nmap d size 0 I type 8. So what does this signature mean? This signature is matched by any ICMP packet that enters the organization's network, that is indicated by this $home net, from the external network, that is indicated by this $external net, and is of type 8. Type 8 ICMP packets are ping packets and has an empty payload, that is d size equals 0. So what is so special about all these characteristics? Nmap, which we discussed in the previous lecture, generates ping packets with these specific characteristics. Hence, this signature is designed to detect Nmap ping sweeps. So if an attacker is trying to scan the network using Nmap, then Nmap will send a sequence of packets with all these characteristics, and using this signature, an IDS can find out that it's probably an Nmap packet. So this is an example of a signature which can be used to detect network scanning. In general, a signature may be a list of characteristics about a single packet. For example, source and destination port numbers, protocol type, and a specific string of bits in the packet payload. Or it may relate to a series of packets. So for example, there may be a series of some 5 packets, each of which has part of a virus payload. A signature may pertain to one packet or it may pertain to a series of packets. Signatures are normally created by skilled network security engineers who research known attacks. So these engineers they study attacks that are launched by malicious users on networks, and they examine the kinds of packets that are sent into the network by these malicious users, and by examining such packets, they create signatures which can be used in the future by IDSs to match with the traffic that they observe and detect attacks. A signature-based IDS operates as follows. It sniffs each packet passing by it and compares it with each signature in its database. There may be tens of thousands of signatures in the database. If a packet or a series of packets matches a signature in the database, then the IDS generates an alert. Here are some examples of detection by a signature-based IDS. Suppose an attempt is there to establish a TCP connection from an external host to an internal host at an unused destination port. So what does this indicate? It may indicate an attempt to find out which services are open. So some attacker is possibly sending packets to different port numbers, and when it receives a response, it knows that there is an application process at that port number. So this may indicate an attempt to find out which services are open. That is, there are processes at which port numbers. So this is a kind of scanning which can be detected using a signature-based IDS. If a specific byte sequence is present in the application payload of an incoming packet, then it may indicate an attempt to inject specific malware, for example, virus or worm. So this byte sequence may be a part of the virus or worm. So that may indicate that there is an attempt to inject such malware. So by matching the specific byte sequence with one of the signatures, the IDS is able to detect the presence of a virus or a worm. An attack that is undetected by a signature-based IDS is called a false negative, and an IDS is said to generate a false positive if it raises an alarm even when there is no ongoing attack. So both false positives and false negatives should be minimized. For example, the false positive rate should be less than 1% or 5% or so. Similarly, the false negative rate should be less than 1% and so on. So we typically have targets about how much we can tolerate false positives and false negatives. But there is a trade-off in doing this. If we reduce false positives, then typically that is at the expense of increased false negatives and vice versa. So here's an example. Suppose packets containing a certain worm need to be filtered out by a signature-based IDS. So the worm accesses a file called run.exe, and the worm payload includes this file name because the worm must access that file. So the file name is included in the worm's payload. The IDS could be configured to filter out packets containing the string run.exe. So this will detect the worm, and it detects the worm by looking at the presence of this string run.exe. But there is a disadvantage of doing this. Innocuous packets which contain strings such as xrun.exe, rerun.exe, and newrun.exe, these will also be filtered out because this string run.exe is present in all of these innocuous packets. So these packets will also be filtered out, and that will result in false positives. Actually, the packets are not malicious, but the IDS flags them as malicious packets. So hence there is a false positive. So such false positives can be eliminated by making the search string more specific and changing it to the full path name, that is /winxp/system32/run.exe. But now the attacker can cause a false negative to occur by using the following equivalent path name in the body of the worm, that is /winxp/system32/... refers to the parent directory, and then again system32, and then /run.exe. So this path name is refers to the same file as this path name refers. But the search string that is used in the signature database, that matches only this string. So it does not match this string. So hence this payload will not be detected, and that will cause a false negative to occur. So via this example, we see that there is a trade-off between false positives and false negatives. So if we make the string for comparison very general, such as run.exe, then there will be a lot of false positives because strings such as xrun.exe, rerun.exe, and so on, these will also be matched. But if we make the search string very specific, then some strings such as this one, they will not be matched by the IDS. So hence there will be false negatives. So this shows that there is a trade-off between false positives and false negatives. Signature-based IDSs have a limitation. They require previous knowledge of the attack to generate a signature. So some security researcher must analyze an attack and analyze the kinds of packets that are sent during the attack, and then create the signature. Only then in the future that attack can be detected. So for this reason, signature-based IDSs are unable to detect attacks that have not yet been recorded. Since each packet needs to be compared with an extensive collection of signatures, the IDS can become overwhelmed with processing, and hence it can fail to detect some malicious packets in a timely manner. So part of this problem is alleviated by having multiple IDS sensors. So each sensor only sees a part of the traffic that flows into the organization's network. But despite this, since each packet needs to be compared with an extensive collection of signatures, the IDS can become overwhelmed with processing, and hence it can fail to detect some malicious packets in a timely manner. So, this is another limitation of a signature based IDS. So, we have discussed signature based IDSs. Another kind of IDS is anomaly based IDS. It does not operate by matching the packet's payload with some pre-stored signatures. Instead, it analyzes the statistics of the traffic that flows through the network. It stores the statistics of the traffic that is observed during normal operation, and it looks for packet streams that are statistically unusual. For some examples of statistically unusual traffic streams are as follows. One example is a large percentage of ICMP packets. So, if the percentage of ICMP packets is usually below a certain threshold, and then suddenly the percentage of ICMP packets is above that threshold, then that may indicate a statistically unusual packet stream. What is the advantage of anomaly based IDSs? They don't rely on previous knowledge about existing attacks, so hence they can detect new attacks which cannot be detected by signature based IDSs. They can potentially detect new and undocumented attacks. Some examples of anomalous packet streams are as follows. Suppose there is a tenfold increase over the norm in the number of accesses to a specific file, then that may indicate that a denial of service attack is happening. So, this is an example of an anomalous packet stream. If the login frequency to a particular account is unusually high, then that may indicate that someone is trying to break into that particular account. So, that attacker is trying out different passwords and trying to log into that account. If the number of distinct source IP addresses of packets arriving into the organization's network from outside is very high, then that may indicate a distributed denial of service attack. So, we discussed earlier how a distributed denial of service attack is performed. An attacker initially compromises a lot of hosts and enrolls them in what is known as a botnet, and packets are sent from all these compromised hosts to the victim. So, in a distributed denial of service attack, the number of source IP addresses of packets arriving into the organization's network from outside will be very high, and this can be used to detect the attack. If the ratio of the number of TCP SYN packets to the number of TCP FIN packets in a time interval is much greater than 1, then that may indicate a SYN flooding attack. So, recall that every TCP connection starts with a three-way handshake, which includes TCP SYN packets, and the connection ends with TCP FIN packets. If the ratio of the number of SYN packets to the number of FIN packets is much greater than 1, then that indicates that an attacker is trying to send a lot of SYN packets to create a lot of half-open connections. So, this indicates a SYN flooding attack. So, recall that earlier we discussed that SYN flooding attacks can be defended against using the mechanism of cookies. This is another way in which we can defend against SYN flooding attack by the use of an anomaly based IDS. But anomaly based IDSs also have a disadvantage. It is challenging to distinguish between normal traffic and statistically unusual traffic. Some challenges in distinguishing between these kinds of traffic is some challenges are as follows. The IDS will have to learn over time what constitutes normal activity, and this can be challenging. The definition of what is normal may vary as a function of time of day or day of the week. For example, the kind of traffic that normally flows in a network during mornings may be different from the kind of traffic that flows at night. And similarly, the traffic on weekdays and weekends may be different. So, hence the IDS will have to learn what is normal activity, and this normal activity varies with time of day or day of the week. What is normal may also vary from one host to another, since different users have different traffic patterns. So, traffic that is normal for one user may not be normal for another user, and vice versa. So, for these reasons, to date, most IDS deployments are signature based, but some IDSs also include anomaly based features. So, we have discussed the classification of IDSs based on detection method. So, the classification was signature based IDS and anomaly based IDS. Now, we discuss another classification based on where the IDS resides, whether it resides in a host or in a network. An IDS that captures information about packets flowing through the network is referred to as a network-based IDS. For reasons of performance, it is common to have standalone appliances that perform network-based intrusion detection. So these standalone appliances only run the IDS, and hence they are not vulnerable to malware attacks. So if we had an IDS which ran in software on a PC, in that case, its performance would be low. In contrast, if we have a standalone appliance that performs network-based intrusion detection, then that typically performs faster than an IDS which is running in software on a PC. So a network-based IDS typically is deployed at multiple points in a large organization. In the previous lecture, we discussed an example network architecture in which there were 3 IDSs. A host-based IDS is typically implemented in software and runs as an application on a host. So it monitors the internal behavior of the host. For example, it analyzes the sequence of system calls that are made and the files that are accessed and so on and so forth. A host-based IDS makes use of the following to identify events related to an intrusion. The IDS looks at operating system logs, application logs, and so on. So the operating system logs, as the name suggests, they have information about the operating system, that is log information about operating systems, and application logs have log information about applications. The operating system logs keep track of when users log in, the number of unsuccessful login attempts, commands executed, network connections made, and so on and so forth. And application logs keep track of the events that are logged by an application during its execution. For example, which files it opened, which system calls it made, and when. So such kind of information is analyzed by a host-based IDS. Keeping track of modified files can play a key role in host-based intrusion detection. For example, a change in the contents of core system libraries should cause suspicion because these are rarely modified, if ever. So by detecting the modification of files, a host-based IDS can infer that some malicious activity is going on. File system integrity checkers compute a cryptographic hash on the contents of each file, and they compare the computed hash of a file to its stored hash. So when a system is initialized, the integrity checkers, they compute a cryptographic hash of the contents of each file and store that hash. Later on, from time to time, they compare the cryptographic hash of the file with the pre-stored hash, and if there is a discrepancy, it indicates that the file has been modified. And depending on the kind of file, that may indicate some malicious activity. For example, there should rarely be any change in the contents of core system libraries. So if there is a mismatch in the hash, then that indicates that there is possibly an ongoing malicious attack. So this summarizes the operation of a host-based IDS. So in summary, we discussed different types of intrusion detection systems. We discussed signature-based IDSs and anomaly-based IDSs. So based on the detection method, IDSs are classified into signature-based IDSs and anomaly-based IDSs. And we discussed network IDSs and host-based IDSs. So depending on where the IDS is deployed, they are classified into network-based IDSs and host-based IDSs. We'll continue our discussion of IDSs in the next lecture. Thank you.